And welcome. Today we're going to talk about the Cauchy-Goursat theorem. This is a very important theorem, probably one of the most important theorems we're going to talk about in this class, and it has to do with the antiderivative theorem that we've talked about before. So let's recall that theorem really carefully here. So we have this theorem that if f of z is continuous, then a series of statements are all true or all false. But in general, once you find your way into one of these statements and assess their truth value, then you're good. So let's talk about the first one. There's A, which was that there exists some antiderivative, capital F, which means that if you take the derivative of it, it's equal to little f. Okay, and we know that that is the same as saying that if I take any contour integral of f, I can evaluate it at the endpoints. I can evaluate the antiderivative at the endpoints and take the difference. And that is for any path. In D, okay, and that's what we call a statement B. And this statement also is what I'll call independent of path, or rather, I can also call that IDP for short. All right, and then we have this third statement, which is that if I have an integral over a closed path, I'm going to call that CL, and that means closed, of f of z, d, z. Those are all any closed path integral is always 0, and I'm going to call that statement C. And we have this enchainment of relationships where each one implies the other. All right, so let's think about this again. So most of the time, though, we're going to start with if I'm faced with some sort of integral, C, integral over some contour. The first thing I'm going to do is, I'm going to look for f, a function f, such that f prime is equal to f. And then I know I have these other two theorems in my front pocket. Okay, so that's typically how we use this theorem. So when the goal here is to compute this integral, we're going to look for a capital F. So we're going to try to find an antiderivative in the domain of interest. Okay, so the idea, though, is that, so we have this, and I want to get a big perspective here. We have f of z, and the only thing we know about it is that it's continuous. So what we do is, and I like to think of this as kind of on a spectrum of things, right? So, and then we have, what we're going to do is then, when we look for capital F, we want to find some function, capital F of z, such that when I take the derivative of it, I get to z, or I get to f of z, right? All right, but we know, and so what we're doing is always, we want to look this way and see if I can find an antiderivative. And then I get this whole host of really nice properties that we can use to compute integrals with. The next question then, and we've been studying this a lot, is what if f of z is analytic? Okay, so obviously analytic is a much more stringent condition than just being continuous, right? Okay, so that is f prime of z exists on D, okay, our domain of interest, all right? That's what analytic means. And that means I can do another one of these, d dz to f prime of z, okay? And so we also call this capital F prime of z here, right? And the question is, what does that bias anything? Okay, so it turns out it does. I better, I'm going to erase my little box here. I'm going to put a give myself a little room here. Okay, And I'm going to state a theorem, and then we're going to at least partially prove it. Not fully prove it, but partially prove it. And I'll state this theorem. And it turns out the theorem basically states that, yes, analyticity of f buys you a whole lot. Okay, so what we're going to state is if f of z is analytic on D, and CL is a closed path in D, then the integral of f on our closed path CL of z, dz, f dz, is equal to 0. So in fact, we can restrict this a little further and just say that we can take our CL here, our simple closed path, CL, and make our domain just be analytic there, so that we can call that our domain. All right, so if that domain, including, so we can call this region inside of here R, if you will, and on that domain, then we get this closed path, which is precisely what we have here, right? So what we have then is an extension to this implication chain, which is that if I know this additional fact, which I'll call D, that f is analytic, it implies this. Okay, so now we have an extension here. So we have a new way into this, all these nice properties of independence of path, of integrating to 0 and closed contours, and the existence of a partial of an antiderivative of our function. So what this means is that f analytic buys you all of this, because now we have an entry point into this really nice enchainment of properties. Okay. So let's now go ahead and do at least a partial proof of this. So again, we're going to start with, okay, so this is our proof. And it's going to be a partial proof. It's going to be a nearly complete proof, and I'll show you what we don't quite prove, but we're going to leave it at that because I don't want to get too bogged down in proving everything. All right, so we're going to say that f is analytic. So that's the supposition, and that means, of course, that f prime of z exists. And we're going to say that, and also let CL be a subset of D. Okay, and we know that f is analytic on all of the region, including. So what we're going to say then is that we have our set D, and f is analytic on the whole thing, and here's our CL. All right, so we can restrict just to the area around CL, and there's our closed path going around. Okay, all right. So I should say on D. Okay, all right. So now what we can do is actually write down. So if I have CL, I can write it as of z of t, and that defines the parameterized contour integral for t being our parameter t a to b. So I can write then this as, I can write that'll be CL again, dz. I can write it as our constructive integral from a to b of f of z of t, z prime of t, dt. And now let's recall then that what we're talking about here is integral from a to b. And now remember, f is actually u plus I v, and z prime is actually x prime plus I y prime, right? So we can actually, when we're looking at this, I can expand it out to be u times x prime minus v times y prime, right? And that's the real part. And then we have a plus I, and then we have in parentheses there a u times y prime plus v times x prime, and the whole thing there is dt. Okay, so we can break this up into two pieces. So we have actually now two real valued integrals, u x prime minus v y prime dt plus I integral a to b u y prime plus v x prime dt. Okay, so now let's try to understand a little more clearly what's going on here. And note that now I'm going to talk about this vector here. I'm going to talk about the vector. So these are actually real valued integrals, but we can take this vector, we'll call it, I'll put it in angle brackets, u comma negative v. I'm going to call that a vector field. All right? And then I'm going to call, and then what we have here then is, and I'm going to have this vector field here too as well. Another vector field, which I'm just going to call u comma, other way around, v comma u. Okay, that's another vector field. All right, so we have two different vector fields. And note that this right there looks like this part down there, and I'm going to kind of go through my statement here, actually looks like a dot product, integral a to b, of the dot product u comma negative v dotted with our vector field x prime y prime dt. Okay, and then I go plus I integral a to b of now our vector field u comma v comma u dotted with, again, the same thing, x prime y prime dt. Okay, so now we have a new way of writing what we've already had before. And now what we're going to do is I'm going to have to go to another page here. Unfortunately, I couldn't fit this all on one page, so we'll redo this now. So I started with integral CL f of z dz, and I got to this point, integral a to b of u comma negative v dot with x prime y prime dt plus I integral a to b of v comma u dotted with x prime y prime dt. Of course, we can rewrite this a bit, and note that if we call r the vector now to be x comma y, then of course dr is going to be equal to x prime y prime dt. Okay, and so we can rewrite this as then integral from along the path. Now we're doing vector calculus here of our vector field u comma negative v dotted with dr. Okay, likewise we have an I integral along our path, again CL, okay, of v comma u dotted with dr. Okay, so now we have a closed path. Oh, I forgot to note that this is a positively oriented path. That is important, although not particularly important here. It turns out to be less important, but we just want to make that concrete at least. All right, so now we're doing vector calculus here. So this is a line integral. Actually, I'm going to call it, it's a line integral, which I'm going to call a what I call a work integral along against this vector field, right? So this is also another work integral, okay? And so we have a really important theorem now. Anytime we have a work integral, an integral of the form where we have some vector field dot dr along some closed path, we have what's called Green's theorem. Which is that if f is equal to some p comma q vector field, if the vector field has continuous partials, that is px, py, qx, and qy are continuous, then we can rewrite our integral as over the region, which we'll call D. So again, we have our path, our CL. The region inside, I'm going to call R. I'm going to call that region inside R. Then we can rewrite this work integral on the path, the counterclockwise path going around that, provided our partials are all continuous and they exist on the domain. We can rewrite it as the integral over a double integral, an area integral over there of the scalar valued function qx minus py dA. All right, so that's a double integral, an area integral, and so we can use this theorem to do our work. Okay. So let's now use this theorem on these integrals. All right, so we'll go to another page here. So again, what we have here is this path integral dz is now equal to the integral. This is CL. That's CL over u comma negative v dot dr plus I integrals CL of v comma u dot dr. Okay, so that looks pretty good. Now what we're going to do is use Green's theorem on both of these integrals. All right, so in this case, that's our p and that's our q. So what we're going to write then is, for this integral, we're going to write this as the area integral over the region enclosed by the closed path. Okay, and then we have a negative vx minus u y. Okay, that's our scalar valued integrand dA. So that's, again, we have our closed path. And that's CL, and the region inside is all that stuff there, plus I area integral over the region of ux minus vy, all times dA, a little area differential. Okay, so now remember, we have this we've assumed that f is analytic. Therefore, ux, or I should say, therefore, the Cauchy-Riemann equations hold. Okay, and that means that ux equals vy and uy equals negative vx. All right, so with these integrals then, we have, if I can replace negative vx with uy, so we get a uy minus uy dA plus I integral, double integral over the region of ux minus, and vy then, of course, is ux, so that's ux dA. Right, so clearly the integrand is 0 there, and the integrand is 0 there. Using the assumption of analyticity, we were able to achieve that inference. And of course, that means this whole thing is 0. So what we have there is so just by knowing that a function is analytic and using Green's theorem, we're able to establish that, that the integral around a closed path is 0. So this is really powerful. So let's now, just one little caveat here. We had to assume that Vx and Uy and Ux and Vy have continuous partials. Okay, And so that may not necessarily be true, and we'll revisit that idea first. But we had to have that assumption. In general, we had to assume that these had continuous partial derivatives in order for this to work. But it turns out you don't even need that assumption. And so a full proof of this theorem would go in and remove that assumption. We could remove this assumption here. But for our purposes, I think we can let this rest. It turns out to not be an issue anyway. So what we have now is a proof to the theorem. All right, so let's now just talk about an example. All right, let's talk about the function f of z is equal to e to the negative z squared. All right, so this, of course, for z that's an element of the reals, right? This is, of course, a Gaussian. And we all know that so now if I want some closed path, let's say I take my closed path to be somewhere in the, and so this is, we know this is analytic entire. Okay. Because it's a composition of analytic functions. And this is a very important function. It's a Gaussian. So if I take this to be any closed path in the complex plane, here's my complex plane, here's my path, going around like that. So the question then is, I want to compute CL of e to the negative z squared, dz. So before the Cauchy-Goursat theorem, I'd have to, of course, I need to search for an antiderivative. So the question is, can we find one? And the answer is no. Certainly an antiderivative exists, but no, but it's not expressible in any simple way. We can't just find one easy. So I have no closed form expression for finding an antiderivative of e to the negative z squared. But, so I can't use the theorem from before. I can't use the antiderivative theorem to compute this. But e to the negative z squared is analytic. So therefore, by Cauchy-Goursat, we know that any closed curve here has to be 0. All right, so it turns out this is going to be incredibly useful later on. We'll start using this to actually compute some integrals in the complex plane that we can see why this is very powerful, because when we don't have a ready way to compute antiderivatives or find an antiderivative, we can still use it. We can leverage this theorem to help us compute integrals that are very important in real-world applications. But we'll leave real-world applications for another day and just state that this theorem, and I want to again confirm this idea here. I want to write this down again. We have this one statement that there exists capital F such that the derivative of it is equal to f. That's one statement. And we had this enchainment of implications that we had this independence of path statement where integral from z1 to z2 of f of z dz is equal to capital F of z2 minus f of z1. And then we had that integral over closed paths of f of z dz is equal to 0. So now what we have then, this of course was all required inside this dotted box here that f is continuous. But now what we have is a new statement that lives outside of that, f is analytic. With this statement here, then we can, of course, I should say that, of course, if f is analytic, then it certainly is continuous. But this extra piece of information that goes beyond continuity allows us an entry point to all of these other results. So we can conclude if f is analytic, I should say in some domain of interest, then an antiderivative exists. We have independence of path, and of course that all closed contours, integrals over closed contours are 0. Okay, so that buys you a whole lot, and of course checking analyticity is even easier than trying to find an antiderivative, much of the time at least. Okay, so now we have a whole host of results that fall out of this. So in future lectures we'll talk about some applications of this very important theorem. Thank you very much.